Hey everyone, this is John Buck back with another discrete time linear systems video. In today's video, this new video, I'm going to show you an example of using the DFT in Matlab to compute the spectrum of measured data or audio data. Particularly, let me get this to the front. The example I've chosen to play for you today, or play with today, is this one. So we have the sad trombone noise, and particularly we'll look at just the first note of it and how I can do that. So let me pause the video and get Matlab open here, and I will show you how we can process this data. All right, so here we are looking back at our Matlab window. This is our example. I'm using the audio read function to pull in it's an MP3 file of the sad trombone noise I downloaded from the internet. I found a bunch of sites that had different versions of it. And I get two outputs from this. X is the samples in time, and Fs is just a scalar value that tells me what the sampling rate of the signal was. In this case, it was 44.1 kilohertz. And so first thing I'm going to do, I'm going to plot the signal. So again, I plot it, where I'm going to go from 0 up to 1 less than the length, and 1 over Fs converts this into seconds, right? These are samples. I can go back. 1 over Fs is our capital T. So these will move things back to real time in seconds for those plots. And I'll see that the overall signal. And that was what I used to help me pull out. I just want to analyze, I'm going to analyze just the first note out of the trombone sound. So I use this to help me get an estimate of roughly where these things were happening in time, from about 1/10 of a second into not quite 3/4 of a second. So let me, before I get too far ahead of myself, let me do that to pull up the time signal. So let me bring this down onto the window we're looking at. So here's the overall signal. So you can see the 4 notes, right? But these are just, again, the time envelopes, right? You can tell the last note is longer than the others and that they happen at a regular interval. But you don't really see the frequencies in these. If we zoomed way in, we might see something about the periods. But these are, again, being sampled very fast. We'd have to zoom way in to see those. And instead, what we're going to see, well, first, let me show you that the first note that I pulled out. So here's the, make this full screen for a second. So here's the first note of the trombone thing. So if we listen to that, I haven't lost my music player. Where did it go? There it is. So here, just the first note. Right, so there's just the first note in the sequence. And we're going to run that through the DFT. So we're going to compute many closely spaced samples of a frequency, making sure we have enough to avoid any time domain aliasing so that we're protecting the signal. We have to figure out how many samples long it is. Let me get out of full screen mode here if I can. Maybe I just pull the editor up on top of it. All right, so this is my that X1 that I just showed you. I pulled that out. I guess I plotted it down here. So here are the commands to plot that, the first note. And then I need to figure out how big my DFT is going to be, where I'm using NFFT because we're going to use the fast Fourier transform as a clever, fast way to compute the DFT invented by Cooley and Tukey. And so this is a faster way to do it that works especially well when the number of frequency samples is called the power of 2, is a power of 2. And so Matlab gives us these commands where it'll say, I can take the length, tell me what the sort of next power of 2 exponent would be, and I get 2 to that. So this is because we do this so often with DFTs and FFTs, a set of commands that says, find me the next power of 2 bigger than the length of X1. And this idea is called zero padding, this idea that I'm going to take more samples in frequency longer than the length of the signal. It's like I took my finite length signal and put a bunch of zeros at the end. I padded it with those zeros effectively when I take these extra samples in frequency. And then these are the samples in frequency, right? If n is how many I'm going to take, how many values I'm going to take, how many samples I'm going to compute in frequency, I'm going to have that many spaces around 2 pi, and then I'm going to have this vector from 0 to 1 less than the number of samples, multiplying this. So these will be my omegas. And if I go down here, I'll plot that version first. So here's plotting omega I like to normalize the pi out with the magnitude of x1. And so here's the frequency running from 0 to 2 pi. Another thing we do often is we say, well, if the signal is real, we know that its Fourier transform is also symmetric on the omega, is even symmetric in omega. The Fourier transform magnitude is even symmetric in omega. And so Matlab gives us these commands to make things that takes the part that goes from pi to 2 pi, we know is repeating periodically the same thing from minus pi to 0. And so what it does is it takes these two pieces and swaps them around using the shifted version. So FFT shift, x1 shift, this command FFT shift is just basically sort of cutting the deck in half and flipping them around. So it takes the values that would normally go from pi to 2 pi and puts them first, so that because they're going to be the minus pi to 0 versions. And then we also shift our frequency axis by pi to match that. So we have a different omega axis when we use the shifted thing. I'm going to plot it each way to show you the difference. And then these last commands, we go back to chapter 7 and use our relationship saying that I have continuous time frequency is discrete time frequency divided by t. Well, if I divide by t, I'm multiplying by the sampling frequency. And then I'm scaling out the 2 pi to move it back to hertz. And I'm going to plot just the sort of middle part from around 4 kilohertz of this note so we can see what it looks like. So let's see how those figures, we already showed you figures 1 and 2. Let's bring figure 3 down here. Right, so here's this top panel is the one going from 0 to 2 pi. We see it goes from 0 to 2. And we see that the trombone noise actually has a lot of very sharp harmonics in it, as we'd expect from a musical instrument, especially one like a trombone that's a nice big resonator, as these are the harmonics, and they all go from about 0 to 0.2 pi, contains all of them. And then we see them showing up again here as I get close to 2 pi. But again, remember, these are the negative frequencies, the things that would have appeared here being repeated every 2 pi. And so that can be confusing, even though it's mathematically easy to compute it this way. It can be confusing to keep that straight, and that's why we do the shifted version, even though it looks a little confusing at first, is to make a version. This version now goes from minus pi to pi. I've taken everything from 1 to 2 and put it on the left side, is what the FFT shift command did. And so I get a nice symmetric version of my magnitude Fourier transform. Here's my magnitude of x of e to the j omega. And again, frequency is going from minus 1 to 1. So this is minus pi to pi. We see everything's pretty much between minus pi over 5 and plus pi over 5, or 0.2 pi. And we see those nice clear harmonics here. And then the last figure I'm going to bring over, figure 4, is the version where I rescaled the frequency axis to give me back continuous time frequencies. Right, so now when I did that rescaling, this figure goes from minus 4 kilohertz to plus 4 kilohertz. And I can see, again, the same basic shape, these same spikes, these are the harmonics, the same harmonics of the musical instrument, the way we talked about things that are essentially periodic in time. So we can see one of these is here. Let me put the cursor on it. You can see where it is, maybe. Put the tools in, data cursor. So there it is at about 0.296. So this is in kilohertz. So that's just under 300 hertz. Then we go over here. We get one just under 600 hertz. Just under 900 hertz. So these are spaced roughly every 300 hertz apart, are the harmonics of our trombone noise. It's also interesting to note, I think we talked about this way back a long time ago when we first talked about Fourier series. Trombone's kind of interesting because it's Fourier series here, or Fourier transform. The second harmonic is stronger than the first harmonic, and then it drops down from there. So it is a special quality, it gives it the special quality of the trombone note. Okay, so there's a good example for you. Let me see if I can get these back hidden or not. That out of the way too. So again, this piece of example of the program is a good example because it has the fragments you need, for example, in Matlab 2 to look at the Fourier transform of the speech signal you're working on and figure out what different parts of it are looking at different parts where the speech is, where the noise is, and where the tone is in your signal. So I'll put these up on the class webpage in my courses as well, so you have the code to work from as well as this video example explaining the code. All right, so that's all for this time. I'll talk to you in the next video.